Is this working? Test. All right. Hello everyone. Today, the topic that we're gonna cover is the fundamental theorem of calculus. Theorem. So, what this theorem is that the roots of a polynomial are equal to the value of n. N being the exponent on top of the x. Well, it doesn't always have to be x, but generally x. So you have to this might to explain how this works, let's draw a graph first. For example, we had something like x2 squared plus 2x plus 1. Let's graph this, right? This would be a polynomial, but it would have two clear roots. X1 and x plus 1. So this is x minus 1, or x equals minus 1. Now the graph would look something like x minus 1. Something like this. Now, in this case, we only had one root, right? But the importance here is that this is actually not -1. This is actually I. So you probably don't understand what I said, because that's because to explain this, we should look at what the theorem fundamentally talks about itself. So let's bring up the base form of any polynomial, n plus bx n minus 1, comma, 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 plus k. This means that there can be any number of, like, this can be as long as it takes n to reach 0. In the previous case, we had x equals 2, so just simply be b equals 1, x plus k. If it were to be a cubed, it would be b plus x squared plus c x plus k. The reason we need to explain this is because by looking at this, so this value is equal to n, right? If n is equal to the roots, how does this work? So generally, looking at only real numbers, what does the graph of a x squared polynomial look like? X squared polynomial is a parabola, right? Let's say it crosses over the x-axis twice. A root is when a root of a polynomial can be graphed as when it hits 0 on the x-axis. I mean, hits 0 on the y-axis. So in this case, there would be 2 roots, and it's not possible for there to be more than 2 roots. About x3, if we have something that looks like this, we have 3 points of intersection. That means that reflects the fact that this has 3 roots. Let's do the force. The force looks like some kind of M or W, right? How many points of intersection does it have? 1, 2, 3, 4. And it has 4 roots, right? And is it possible for it to have any noticeable points of intersection? No, because even if you move the graph around, like even if you place it like here, there's no way to get more than 4 intersections. You could get less, but not more. This shows that the number of roots, at least for the maximum, it reflects. Now, you might be asking, what if the graph looks like this and it never touches the y-axis? Well, in that case, that's because uh, the roots of the graph are not on the normal plane. So, uh, when you're asked to simplify quadratics, sometimes you get squared plus, yes, squared minus 1. Sometimes you get answers, and the roots can't necessarily be graphed on the main plane. For example, we do this, this becomes x times x plus I, does it? Oh, no, no, no. Be x minus I, and proving this, it's 2 plus ix minus ix minus I squared, which is uh, -1, but you're subtracting by it, so it becomes plus 1. These two cancel out, so it becomes x squared plus 1. So if we see here, we see that the roots is equals, for it to equal 0, x needs to equal either -I or I. Now, how do we graph this on the graph? Well, simply put, you can't. It because these numbers are imaginary. They can't be represented on the imaginary plane. That's why, in this case, the graph would never intersect the y-axis. Like, the graph of x squared plus 1 looks something like this. See how it never touches here? There's this gap of 1, and that 1 prevents it from having a proper root. The same similar rule can be applied for uh, every graph or every polynomial. It's 3. For example, we could have something that intersects twice, twice here, 1, 2, or just once. However, on odd, if n is an odd number, or odd number, a rule is that there always needs to be at least one real root. Because if you think about it, x squared expands in one direction. If a function is even, it all expands in one direction. If you do it this way, you could put it in the middle of the line so that they never approach y. But for odd functions, odd polynomials, they approach infinity in both directions, both infinity and negative infinity. So no matter where you place them on the graph, there's always going to be one point where they touch 0 and hit the real plane. All right, on to the next point. To help understand this, what sometimes help is, especially in the case of where you need to figure out unreal, non-real roots, you probably won't have to do them for anything bigger than n equals 2, but in the case that you're doing something for n equals 2, you can simply just use the quadratic formula. If you don't remember what that is, it's negative b plus or minus negative 2b plus 4. Wait, give me a second. Let me double check this. Ah, never mind. This is not. Forget what I said there. This is b squared minus 4ac over 2a. Now, usually when you if we plug in some examples we had before, you probably all, as we showed, a, b, c equal the coefficients. So using the example we had earlier, squared plus 0x, since there's nothing in the middle, we're going to call it 0 plus 1. If we plug this in, it becomes negative 0 plus or minus 0 minus 4 over 2. Answer to this becomes square root of negative 4 is equal to 2i, because square root of 4 is equal to 2 and the square root of negative 1 is equal to I. So it becomes 2i. So, and this renders plus or minus over 2, so it just becomes plus or minus I. And usually the plus or minus is the determining factor in what makes the n equals 2 always have two roots. You can never have more, you can never have less. That's because the innate nature of plus or minus just doesn't allow for you to have the same answer. Moving on to the next topic. What we're gonna do is that we're gonna move on to division of polynomials. You might have touched on this in Algebra 2 before. So generally, we try to apply the concept of long division. So do you know that format of like 365, and then you divide it by 5? Can we put 5 into 3? Nope. So this is 0. Can we put 5 into 36? Yes, 7 times. So 35 minus 1. So 15 is left. How many times can we put 5 into 15? 3 times. So we get the answer 5 times 73 equals 365. Same concept applies for polynomials. So we usually start with something like something's moderately big. 4 plus 3 plus 2x2 plus x plus 1. Say it's this. Oh. And let's have a, should we put here? Can just simply start with an x here. So put this here. How many times can you put yeah, how many times can you put x into 4x cubed here? Well, If you divide 4x to the fourth power by x, you just get 4x third, right? So now we subtract this by 4x cubed. This completely gives us with 0 and allows us to move on to the next term. Same rule applies, 3x cubed, 3x squared. That turns into 0. We can move on to 2x squared. So we have 2x minus 2x squared, 0. So, and this is 1. Then you're left with 1, which you can't divide by x because it has less x's than the current number. And we leave this as the remainder. Or you can divide it, you can write 1 over x, but you can also just write remainder 1. Usually they prefer to give you this answer, but there might be questions where they specifically ask you for the remainder when you divide. Now, applying the same concept, this is where it gets more complicated. Something random like this. Divide this by x plus 1. So when you work with these, because x is always of the highest denomination, you don't need to account for the 1 when you try to figure out how many times you can put this into this. So 50x, divide 50 cubed by x, so it becomes 50x squared. If you multiply that out, this becomes 50 cubed plus 50x squared. And you're subtracting it, so you make this minus. This gets rid of this, but now you need to subtract this from 4x squared. Even if it overflows onto the next number, like we see here, you can see that we can show you how to do it. 46x squared. So for this, negative 46x. Now here it becomes, because you're multiplying by a negative number, becomes negative 46x, except not because because this was negative, you need to make this both positive again. So now you're down here to this. Ends up being 49x plus 8, and here plus 49. That's pretty simple. And you probably know how to do this, so we can skip this. So this becomes negative 49. 8 minus negative 49 is negative 41. So the remainder is negative 41. Remainder equals negative 41. Or you could write it just at the end, like 41 over 1 plus x. The same rule still applies no matter what you're trying to divide it by, as you can use the same method as long as the thing to the left is of an equal or smaller denomination than the one on the right. This doesn't really work when you're trying to, let's say, divide x plus 3 by x over to the fourth power, because, well, you're already at the remainder point at that point, right? There's no way you can fit x to the fourth into x cubed, no matter how hard you try. What else is there to cover? Let's just do a bit more practice. Maybe with something bigger here. So one of like the most drastic, longest ones I saw was like, the question was divide x6 plus x fourth to the plus. This is like the longest one that I had by. All right. So when you approach these, especially those that have gaps in the middle, you apply the same rule that you apply for the rest of like any polynomial function that you deal with where something in the middle is missing. You have you set up a different one with the coefficient equal to 0. So x plus 3 is equal to third plus 0x squared plus 0x plus 1, and this is equal to 6 plus 0x to the fifth plus 8x to the fourth plus 0x to the third plus 3x squared plus 0x plus 19. You need to have this all out when you try to divide it. So, erasing some of this. Let's try to fit x to the third inside of here. If we try to fit this, if you divide x to the fifth by x to the third, the most obvious thing that comes to mind is, well, x squared. Now that you have that, you have this equal to x to the fifth here. Write out, no matter what you multiply here, it stays 0, so 0 is 0, plus 0, plus 0, and all the way at the x plus 3 is when you get x plus 3. And now we make this entire thing negative to subtract. So these two don't actually do anything, but this gets rid of this. This means nothing. And the only thing that actually changes is x to the third here. See how it affected the x to the third spot of the thing you were dividing it by, even though it didn't originally have one before. To write this out, this becomes fifth, fourth, minus x to the third, plus 3x squared, plus 0x plus 19. In this case, if this is already 0, you can just put this as 0. Because even though you could technically fit stuff into it, it doesn't actually really count. Oh, this is 6. So this would be 3. So in this case, this is just automatically crossed out. Now you try to fit x 8x to the fourth power. X. Pretty simple, right? I mean, we skipped the x2 here, so it's only natural that we would actually just get to x 8x. So this looks something like 0, 0, 8x. So now this crosses it out. This leaves us with negative x cubed plus 3x squared minus 8x plus 19. Try to fit x to the third in here, so we get negative 1. multiply everything by -1, so x to the third plus 0 plus 0, and 1 is multiplied by -1, so a -1 except you make it positive again, so this just becomes +1. This adds up to 20, or so that's up to 3x squared minus 8x plus 20. So this is actually just a remainder, because we've gotten to a point where the thing we're trying to divide by has a uh, larger power than the stuff we have left. We're finished here. So you can kind of take it like this. The number of times you need to divide is equal to uh, the n of the thing you're dividing it by, so n initial minus n divisor. Like in this case, we had to do it 3 times because it was 6 minus 3. Now this is left. You can show this as remainder 3x squared minus 8x plus 2, which is what these types of questions usually ask for. Or you could also just write it as 3x to the squared minus 8x plus 2. Don't forget to read the directions to see what part of the answer they want you to give. The main point is that the main point of this example was that you need to put out these zeros in case to hold the position. You can't just move stuff down, otherwise stuff kind of clashes. For example, if we didn't have these and moved 1 all the way down there, we would have to add like x cubed to 9, which wouldn't make sense at all. That's it for today's lesson. I hope you guys enjoyed the stream and have a nice day.